Hello, Mr. Chan here, about to do a lesson for Algebra 1, 5-1, the absolute value function. Grab your note takers and turn to page 97, and let's get started. Recall from our introduction to the previous lesson, absolute value functions are referring to these two vertical bars, and that refers to distance from 0 on the number line. Let's have a little opener here, explore and reason. Groups of students are hiking from mile markers 2, 6, and 8 to meet at the waterfall located at mile marker 5. So let's take a look at how everything's located relative to mile marker 5. So I'm going to draw some water droplets here to represent the waterfall. We have some students at mile marker 2, 6, and of course 8. Their distances can be quickly measured relative to mile marker 5 by drawing arrows in that particular direction. We see that mile marker 2 and mile marker 5 are literally 3 miles apart. Mile marker 6 relative to mile marker 5 is 1, and mile marker 8 compared to mile marker 5, of course, is 3. How can you use the mile marker to determine the number of miles each group of students needs to hike to the waterfall? Well, we already actually kind of did it on the graph. We went ahead and subtracted the marker numbers. So that's a strategy that we applied just by reading the word problem. And when we subtract them, sometimes we might accidentally get a negative number depending on how we subtract them. So we must have done that particular operation in our heads with thinking of the positive number only. So just make it positive. Those numbers that we are getting are positive distance values. Second question. Make a graph that relates the position of each group on the trail to their distance from the waterfall. Okay, let's do that. Let's draw, since everything's positive, we're going to make it relative to the first quadrant. And we are referring to the students relative to the waterfall. So distance we'll use on the vertical axis. And it's going to be relative to mile marker number 5. And the horizontal axis we'll refer to as the marker number. And we have marker numbers from 2, 5, 6, and 8. So let's put that down. 6, 7, 8. And looks like our furthest distance from 5 is 3, so we'll just do it vertically. And when we plot the points, mile marker 2 is 3 away. We get a pattern. Mile marker 0, of course, is 0 away. We'll just put that right there. Mile marker 6 is 1 away. And mile marker 8 is 3 away. When we connect the dots, we'll get this pattern. It's your V. Absolute value is a V-shaped graph. Oh, sorry, kind of jumped the gun. The word problem itself doesn't mention anything about absolute value, but the graph we get itself is V-shaped. And distance from 0 on the number line, two-dimensionally, will give you that V-shaped graph. And that is linked to this particular section's function called the absolute value. We'll see that more in the next few examples. Kind of jumped the gun, didn't I? Hey, next question. How would the points in your graph from part B change as the groups of students approach the waterfall? So the distance from number 5 when they approach the waterfall would probably get smaller. So quickly, our previous graph looked like this. When the mile markers indicate that they're closer to there, they're approaching different mile markers, the graph itself would start shrinking like this. Does that make sense? So relative to how we think about graphs and transformations, it is actually compressing or shrinking because the points will shift down. As we get closer to mile marker number 5. And eventually, the distance from mile marker 5 with the students will eventually approach 0. Why is the absolute value of a number always positive? How does it relate to real world situations? Explain. Well, we are literally measuring distance from 0. In the real world, distance is always positive. All right, let's move on to the next page. That was a good opener. So I did open the can of worms here already when it comes to describing this particular section's parent graph called the absolute value function. So here it is, ladies and gentlemen, the absolute value function, f of x equals the absolute value of x, distance from 0 on the number line. If we create a little T chart, no matter what we pick for the domain, the distance on the number line from those points will always be positive. The distance of -3 on the number line to 0 is 3, and so on and so forth. That's your range in that T chart. No matter what you pick for the domain, you'll get this range of values that are all positive for the parent graph. And you see where this is heading, don't you? Eventually, we'll get a situation where we will be shifting, stretching, shrinking, reflecting this particular graph, just like we would with any parent graph. Let me plot those 7 points that I have over to the left from the table, and let's see what we get. There it is. My parent is a V-shaped graph. This is the parent graph. Note something interesting. That point at the bottom is the vertex. in terms of vertex form of this absolute value function, I'm going to generically write it down here next to the table. Y equals a vertical bar x minus h closed vertical bar plus k. That looks familiar. A, of course, R is your multiplier. This is a vertical stretch, shrink, and reflection. Shrink is also known as compressions in some books. Please keep that in mind. H is your horizontal shift left and right. K on the outside of the function is your vertical shift up and down. And the vertex itself, relative to this vertex form, is HK. And in this case, it's 0, 0, because that's where the parent starts. When you start throwing in numbers for A's, H's, and K's, it starts manipulating that V-shaped graph, whether it's reflecting it, stretching it, compressing it, or shifting it around up and down, left and right, via the vertex. Some other things we need to talk about. The domain and range. The domain are referring to what x values you can pick. In this case, no matter what x value you plug into the function, f of x equals absolute value of x, you will always get an answer. So here the answer is, for the domain, all real numbers. You can write it with a special symbol, looks like a funny R, like that. The range for the parent graph here are the y values. Hey, look at my column there. All my y values happen to be positive, including 0. So therefore, my range is all y values that are greater than or equal to 0, including decimals and fractions. So those are all the positive numbers and 0. Okay. In fact, if we invoke Desmos, I'll show you. I have some of those graphs ready to go. I have my first equation here, f of x equals absolute value of x. Boom, it is a v. No matter how far you go left and right, I can pick any x values I want to. It is a v. Okay, there it is. Great. Any questions? Let's move on to example 2. We've got some different child graphs here. We're going to be doing some transformations with the absolute value function. And it looks like for this section, we are going to focus on the a value. H's and K's come later in a different section, so we won't worry about them until later. Number 2, how do the domain and range of each function compare with the domain and range of the original parent graph, f of x equals the absolute value of x? So the second example here, we have g of x equals 1/2 x. So if I break out a table, or if I turn on Desmos, first thing I want to do is, of course, plot my parent graph. It's always good to have that reference. It also helps to grade things. So I'm going to put in my parent graph here. And usually 3 or 5 points will do. 0, 0 is where it starts. 1, 1, 2, 2. Those are the 3 points from the parent graph up there in example 1. I'm going to mimic it over here on the left. This particular graph is a symmetric graph. Has symmetry along the y equals the y-axis. And what I'd like to do is to leave those dots there. That's your parent graph. That 1/2 is a value that will affect the parent graph. That 1/2 is your A value. In this case, 1/2 will take a half of all your Y values. That table I have on the left there, those numbers 3, 2, 1, 0, 1, 2, 3, and up here in this column will be cut in half. Literally, what this does is it is a vertical shrink or compression by a half. The height of those points that are red, graph for the parent, will be chopped in half, literally. That corner point right there, 2, 2, that second value, the Y value, will be cut in half because of that 1/2 thing. It will drop to 2, 1. Let me zoom in a little bit so you can see it better. Sometimes I forget to do that. So 2, 2 becomes 2, 1. And the new graph, when you connect it, and if you try to do half of 0 for the vertex, doesn't go anywhere, you will be graphing, it'll look like this. It's like taking that V-shaped graph and smooshing it vertically. And it'll be reflected here on the left as well. Think about it. We're cutting all the Y values in half, and when you plot it, you'll eventually get this V value. Okay? The domain stays the same. All real numbers. The range, the vertex doesn't go anywhere, it's still the same. I know that sounds kind of weird, but if you zoom out, that orange V that's been compressed or shrunk by half still goes up forever. Okay? Let me prove that to you with Desmos. I still have the parent graph right there. And for 2a, let me turn on that function, g of x equals 1/2 x, absolute value. Look at that. Okay. Let me move the graph so you can kind of see how it's been pushed. Okay. Smushed vertically. Now it's almost like an optical illusion. If I show it like this, it looks like it's being stretched horizontally. That's a lesson for another day and why that is also true. And you won't hear about that until Algebra 2. But if I move the graph here to the left edge, look at that. See my mouse here? That orange, actually red, has been smushed down by half down to here in terms of height relative to the x-axis. The height of those points has been cut in half, okay? Okay, I'll turn that off. Let's see what happens with the next problem. Here we go. Any questions about example 2a? 2b, same process. I'm going to go ahead and draw in my parent graph and see what happens. Because my a value is different this time. It's -2. Oh, that's interesting. In the previous example, it was 1/2. In this example, we have -2. What's it going to do is the question. I can use a t-table if I want to again. Any guesses what it'll do? What does the negative do? What does the 2 do? You have to treat them separately, as you know from previous usages of transformations. So let me put in the 5 dots for the parent graph first to get that going. Here's my parent graph. Who's your daddy, right? And we'll pick on 2, 2 again. And of course, 0, 0 from earlier. Those are mainly the 2 points you really need actually for absolute value. And you know what, this time let's make it a surprise. Some of you are already guessing what's going to happen. I'm going to go ahead and jump and turn on Desmos, switch over, and turn on -2 times the absolute value of x. Oh, that's interesting. It's upside down, right? Negative does a reflection. The 2, and if you think about it, this particular V is upside down, but it's also skinnier. That 2 is stretching it by a factor of 2, whereas the previous one was 1/2. That made it smushed. So what I'm going to do is kind of like have you guys focus on this left edge here and see how the parent graph is red. The last example was blue, it got smushed in half. But the third example in 2b is reflected, but it's stretched by double, okay? So that is the relationship there. So it's upside down, and that 2, 2, literally you are multiplying the 2 by -2. That is your A value. 2, 2 becomes 2, -4. It goes all the way down to here. Make sense? 0, 0 stays the same. 0 times anything is still 0. So your graph now becomes this. And it's reflected on the other side as well. Okay? So, in summary, that A value is a vertical reflection and stretch. The domain seems to be the same because you can pick any x value, it'll come out and give you an answer. But my range is now going in the opposite direction. It's going downwards. It starts at 0, but it's going downwards. All my y values now have become negative. Okay, makes sense? Okay. So that little less than or equal to sign is referring to negative numbers and 0. Okay, makes sense? All right. Let's move on to example 3 on the next page. Here we go. All right. Oh, we got a word problem. Example 3. A cyclist competing in a race rides past a water station. The graph of the function d of t equals 1/3 times the absolute value of t minus 60 shows her distance from the water station at t minutes. Wow, this is getting complicated. Assume the graph represents the entire race. What does the graph tell you about her race? So we know from the opener this morning that relative to the water station, or the waterfall, actually this is a water station, the vertex describes how everything culminates. So let's just focus on the vertex of this particular graph right there at 60 minutes. Okay, so that's 60 minutes along the time. Kind of tells you that the cyclist took 60 minutes. Think about that. To ride her bicycle. That's 60 minutes away. To reach that water station. That's how I'm interpreting this particular graph. She starts off relative to 0 minutes, 20 kilometers away. That tells a story, this particular graph, doesn't it? So 20 kilometers away. When she started this race from the water station, right? So that is the relationship, 20 kilometers away from the water station. And it took her 60 minutes to reach it. Make sense? So I didn't really do a lot of math here. I just interpreted the graph itself. All right, let's move on to the next example. The next example is kind of interesting. It's another word problem. The graph's already given to us, but we have to do something called determine the rate of change. Rate of change? That sounds kind of familiar. Well, we've already done this before, you just don't know it. Rate of change is another way of saying, hey, what is the slope? Slope is rise over run. Rise and run, as a formula, you may recall, is y2 minus y1 divided by x2 minus x1. That's the formula for slope m. Just want to remind you when it comes to graphing lines. Let's go and tackle this particular word problem here. Kata gets on a moving walkway at the airport. Then 8 seconds after she gets on, she taps Lisa, who is standing alongside the walkway. The graph shows Kata's distance from Lisa over time. Calculate the rate of change in her distance from Lisa from 6 to 8 seconds, and then from 8 to 12 seconds. What do the rates of change mean in terms of Kata's movement? Now, we're just basically analyzing data here. 6 to 8 and then from 8 to 12 is referring to the t-axis, okay? So we have to do a little adjusting here. The t-axis there is the x-axis. Keep that in mind. And the d of t-axis is also the y-axis. Sometimes we start mixing all these variables in, it gets a little confusing, but t is the x and d is y. We're going to use a formula. Now, we're going to find the rate of change by using the slope formula by identifying the points on that absolute value function. From 6 to 8 seconds, let's go ahead and identify that particular window. Here's 6 seconds, and here's 8 seconds. Between 6 and 8 seconds, the distance away between Kata and Lisa can be graphed like right about here. And here. Okay? So those 2 points we're going to identify as point 1 and point 2. Doesn't matter which one you use as long as you're consistent. Okay? Let's go ahead and find the rate of change from 6 to 8 seconds. Here we go. I'm using the formula up there. The coordinate points of those 2 points are 6, oh my, identifying 6, 4 for the first point, and it goes to 8, 0 for the second point. I'm going to plug those into there. Here we go, y2 minus y1. Okay, the y value of the second point is 0. The y value of the first point is 4. Great. x2 is 8. x1 is 6. Do a little math there. That gives me -4 over 2. That gives me -2, like that. Okay? Ah, I just realized something really strange. In your graph, in your note taker, they have 6,5. Interesting. So going by what I did last year, we just made a small error, assuming that was 6,4. I'm going to change that to 6,5. I apologize, to kind of match the notes from last year. Not a big deal. It's going to change my calculation slightly, but to kind of coincide with what the authors interpreted this graph, it is true. It doesn't look exactly 6,4. The graph is a little bit stretched upward. They call it 6,5. That's fine by me. No big deal. We're just going to change that to 0 minus 5. That gives me 5. -5 over 2. That will give me -2.5. In this case, seconds per feet. Okay? Feet per second. Sorry. Those are my units. Sometimes these things happen when we're trying to interpret graphs. This is a great lesson. And maybe subconsciously I purposely or not purposely made that mistake, but we caught it in time. So that's -2.5 feet per second. So distance we know is not negative. So one way of saying is this. It doesn't matter if you're going left or right. It's still technically, officially 2.5 feet per second. I'm making that a positive value. How about going the other way? When Kata starts moving away from Lisa from 8 to 12 seconds. From 8 to 12, that point up there, and I'll tell you what the book says, so we don't get our numbers mixed up. It's 12 comma 10, okay? And yeah, I can call that point 1, point 2, point 1 again, but it doesn't really matter. Just keep them all lined up. If I find the rate of change from 8 to 12 seconds, let's see what that is. Is the answer different? That's the question. Here we go. Let's plug the numbers in. Always like work from left to right. So my y2, meaning my 0.2, or in this case, is always the number on my right, whereas the first point is always on my left. So it's a good way to look at it that way. So we have 10 minus 0 over 12 minus 8. And that gives us 10 over 4. That reduces to, 2.5, yay, feet per second. So because this is a moving walkway, it shouldn't have different acceleration. It should be the same velocity, right? Same, no acceleration at all. Your answer should match. All right. I think we're ready for the last example, last page, I'm sorry. Any questions on this page? Let's go and do that. Move to page 100. Here we go. Find the domain and range of each function. So far today in this lesson, we've been dealing with the a value. And in terms of a values, let me remind you of that. We haven't dealt with h's and k's yet. Kind of jumped the gun because we've done that with previous parent functions before. The a value seems to modify the v-shaped graph, either stretching it or compressing it or reflecting it. That 5 is kind of like the 2, or the 1/2. It's a multiplier. Think of the 5 as like 500%, right? So right away we can invoke Desmos or just kind of use a table if you want to, which is probably very inefficient, but let's go and take a look at what happens when we have thrown a 5, okay? So here we go. Here's your 5. Boom! There it is. It's in purple there on the graph. It is a stretch of 500% right there. Okay, great. So let's go back to our notes here. Do a quick paragraph. And the 5 stretches it way out there by 5. What? My point at 2, 2 from the parent graph goes to 210, right? 2 times 5 is 10. Woo! So it's interesting they want us to ask to do the domain and range. No big deal. The domain happens to be the same, all real numbers, and the range is still above the x-axis. And those my y values are all positive or 0. There it is. Great. Number 6. Strange. Looks kind of familiar, right? Well, we don't have to do number 6 because it's the same as example 2b from the previous page. We can skip that. All right, moving on to number 7. These problems are not that exciting, but 1.5 is basically 150%. So let's go and graph it. Throw in my parent graph. And eventually I will be multiplying my 2, 2 or 1, 1, doesn't matter which one you use, by 1.5. This is a vertical stretch by 1.5 or 150%. Yeah, that's a great way of thinking about it. That's 150%, yeah? So 2, 2 goes to 2 times 1.5 is 3. And just connect the dots. 0 goes nowhere. So there it is. And we're going to reflect it on the left side there. It's symmetric. Yay. They don't ask for the domain, that's okay. But there's my answer right there. Number 8. Our multiplier A is negative 0.8. We know from before, negative is a vertical reflection because you're affecting the y value. And this is a vertical. Now be careful with the 0.8. 0.8 is less than 1. 0.8 is a shrink. It's basically 80% versus 100%. 80% makes it small. This is the vertical shrink by 0.8. Think of it as 80% of the original, yeah? Let's go and go through the motions of applying these particular transformations. Always draw on your parent graph first. Best way to get going there. Who's your daddy there? And 2, 2 is a great place to start. 2 times 0.8, negative 0.8 is going to be negative 1.6. So what I'm doing is I'm going to multiply this by my A value. And when I do that, I get negative 1.6. And it's upside down, yeah? Negative 1.6 is right about there. And there it is, ladies and gentlemen. It's upside down and it's shrunk. Yay. All right. Last one. Oh, we're looking for rate of change, also known as slope. They tell us to look between, this is a compound inequality, by the way, interesting. Rate of change is slope. And we're looking between 15 and 18. Now, I don't have the exact numbers here, but let's look. Oh, they've already kind of highlighted everything. That's fine. The points themselves are not great. Look at that. I don't know what the heck that number is right there. We don't know. It kind of looks like 15.5. I don't know. And this point right here, even worse. That's 18, I don't know, almost 5, 4.8-ish. Great. I think the point is this. Rate of change is slope. y2 minus y1 over x2 minus x1. I'm not going to finish this problem. I'm just going to set it up and put those numbers in, okay? And we'll call this point 1, point 2. We'll just put the numbers in. Whatever it is, it's not going to be perfect, but it's close enough. 4.8 minus 5 over, did I do this right? y2 minus y1. Oh, I call that 5? That's kind of weird, awkward. That is not 5. That's wrong in the note. Interesting. I might have to correct that on my notes from before. That is about 3. Sorry about that. That definitely is 3. Ha, 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 ha. Okay, so I don't know where I got 5. Let's put that in. 0.85. Good thing I caught myself, yeah? That's definitely a 3. Over 18 minus 15. We might as well finish this, I guess. 4.8 minus a 3 is 1.8 over, oh my gosh, I can't believe this. What are the chances? 18 minus 15 is 3. No way. My rate of change looks like 0.6. That's assuming that my 4.8-ish is exact. Any questions? All right. Well, thank you very much. I hope this helps you guys out. See you guys next time. Bye-bye.